4 light years away, 3 stars are pulling on each other in a slow cosmic dance. One of them might hold a planet with oceans. It is the closest star system to Earth, and you will almost certainly never see anyone reach it. We are going to travel through frozen astronauts who never wake up, dust grains that hit like bullets, and a laser array more powerful than every reactor on the planet combined. If this kind of cosmic mystery grips you, hit subscribe so you do not miss what comes after. The numbers are about to get very uncomfortable. Hold tight, because the truth about Alpha Centauri is harder than science fiction ever admitted. Look up on a clear night in the southern sky, and you might spot a bright point of light near the constellation Centaurus. That single dot is actually 3 stars locked together by gravity, and they are our nearest neighbours in the entire galaxy. Their names are Alpha Centauri A, Alpha Centauri B, and a tiny red dwarf called Proxima Centauri. Together they form the closest star system to Earth. For centuries, astronomers dreamed of the day humans would visit them. The idea feels almost reasonable. After all, if these stars are the closest, they should be the easiest to reach. Right? Wrong. Catastrophically wrong. The distance between Earth and Alpha Centauri is so vast that human language barely has the tools to describe it. We can write the number down, we can say the words out loud, but the moment you try to actually picture what that distance means in physical terms, your brain quietly refuses to cooperate. Here is one way to start grasping it. Imagine shrinking our entire solar system down until our home star becomes the size of a grain of sand sitting on your kitchen table. In that scale, Earth would be a microscopic speck orbiting just a few inches away. The outermost planet would be barely a foot from the grain. Now, where would Alpha Centauri be in that same model? Not in your kitchen, not in your house, not even in your city. It would be roughly 40 miles away, a grain of sand on your table and another grain of sand 40 miles down the road. That is the emptiness of interstellar space. That is what nothing actually looks like when you measure it honestly. And yet this is the close one. This is the easy target. Every other star in our galaxy is even farther. Some scientists call Alpha Centauri the doorstep of the cosmos, but that comforting phrase hides something darker. A doorstep implies you can step across it. The truth is that no human-made object has ever come anywhere close to crossing this gap. Our fastest probes, travelling at speeds that defy imagination by ordinary standards, have barely scratched the edge of what we call interstellar space. The Voyager spacecraft, launched in 1977, are still considered humanity's farthest emissaries. After nearly 50 years of constant motion, they have only just begun to leave our local solar bubble. At their current speed, if either Voyager were aimed directly at Alpha Centauri, the journey would take more than 70,000 years. 70,000 years. That is longer than written history, longer than agriculture, longer than the wheel. By the time the spacecraft arrived, civilizations would have risen and collapsed dozens of times. The English language would no longer exist. The descendants of whoever launched the probe might not even remember why it was sent. This is the brutal opening fact that every interstellar dream has to face before anything else. Distance is the first wall, and it is also the gentlest wall. Because as you are about to discover, even if we somehow built a ship that could shave that journey down to a few human lifetimes, a much stranger problem appears. A problem hidden inside the very fuel that would have to power the trip. Numbers in space are slippery. People hear them, nod, and forget them 5 seconds later. So let us throw away the scientific units for a moment and translate the gap to Alpha Centauri into something your body actually understands. Start with walking. The average person walks about 3 miles per hour. If you started walking from your front door right now and somehow built a perfectly straight road through space, never stopping for sleep, food, or weather, you would reach Alpha Centauri in roughly 900 million years. That is twice as long as complex life has existed on this planet. Try driving instead. A car cruising on the highway covers about 70 miles per hour. Hop in, fill the tank, and start the engine. The car would arrive at Alpha Centauri in around 40 million years. The dinosaurs went extinct 65 million years ago, just to give you a sense of how absurd that timescale is. Maybe a jet plane will help. A commercial airliner flies at roughly 550 miles per hour. Strap into a window seat. Order the chicken or the fish. The plane would land at Alpha Centauri in about 5 million years. Modern humans have only existed for around 300,000 years, so the species that climbs off the plane would not be us. The Concorde, the supersonic jet, flew at over 1,300 miles per hour. Even at that legendary speed, the trip would still take more than 2 million years. Faster, yes, but still completely meaningless on a human timescale. What about a bullet? A high-powered rifle round leaves the barrel at around 1800 miles per hour. Fire it straight at the stars. The bullet would arrive in about 1.5 million years, assuming nothing got in its way. Which it would, but ignore that for now. Things start getting interesting only when you reach genuinely extreme speeds. The International Space Station orbits Earth at roughly 17,500 miles per hour. That is fast enough to circle the entire planet in 90 minutes. Surely a vehicle moving at orbital velocity could close the gap. It would take about 170,000 years. Even the Apollo spacecraft, the machines that carried astronauts to the moon, were sluggish by interstellar standards. Apollo cruised at roughly 24,000 miles per hour. From Earth to the moon in 3 days. From Earth to Alpha Centauri in around 100,000 years. The fastest object humans have ever built is the Parker Solar Probe. It currently holds the speed record at over 430,000 miles per hour during its closest approach to our star. That is mind-bending velocity. A single second of Parker Solar Probe travel covers more distance than a passenger car covers in 9 hours of highway driving. And yet, even this record-breaking machine would still need around 6,500 years to reach Alpha Centauri. 6,500 years. The pyramids of Egypt are about 4,500 years old. So if Pharaoh Khufu had launched a Parker Solar Probe at the moment construction began, the spacecraft would still have another 2,000 years to go before arrival. The lesson is brutal. Every conventional speed humans can produce is laughably slow against this distance, which forces a desperate question. What if we built something far more powerful, fueled by the strangest substance in the universe? The Voyager twins are the most successful interstellar messengers humanity has ever launched. They were never meant to reach another star. Their original mission was to fly past the giant outer planets and send back photos. Once that work was done, engineers pointed them outward and let them coast into the dark. Today both probes are still working, sort of. They send back faint whispers of data from over 15 billion miles away. Their power is fading. Their instruments are shutting down one by one. Within the next decade or so, they will fall silent forever, but their bodies will keep drifting through space for billions of years. Voyager 1 is moving at roughly 38,000 miles per hour relative to our star. That is fast enough to circle the Earth in about 40 minutes. Imagine a craft so swift that an entire continent passes beneath it in the time it takes to brew a pot of coffee. Now point that speed at Alpha Centauri. The journey would take approximately 73,000 years. Stop and think about what that number actually contains. 73,000 years ago, our species was sharing the planet with Neanderthals. Cave paintings had not been invented yet. The wheel was tens of thousands of years away from being imagined. If a Voyager-class probe had been launched at that moment by some mysterious ancient civilization, it would only now be arriving at our nearest stellar neighbour. The probe would witness the entire history of human language. Every empire, every war, every song, all while drifting silently through nothing. Why is the Voyager so slow when it sounds so fast? The answer comes down to physics. Our probes get most of their speed from a clever trick called gravity assist. They fly close to giant planets like Jupiter, and the planet's gravity flings them forward like a stone from a slingshot. But there is a hard ceiling on how much speed a slingshot can give you. Once you have used Jupiter, Saturn, and a few other helpful giants, there is nothing left to push against. The probe coasts. It does not accelerate anymore. It simply drifts forever at whatever speed it had when it left the last gravity well behind. So Voyager is moving as fast as it ever will. There is no engine still firing. There is no fuel left to burn. It is essentially a thrown rock, and the rock will keep travelling at the same speed for the rest of its existence. Engineers have proposed faster probes. Some designs call for using our own star as a slingshot, swinging in dangerously close before flinging outward. These could potentially triple Voyager's speed. Even so, the trip to Alpha Centauri would still take over 20,000 years. Other concepts involve nuclear pulse propulsion, where the spacecraft is literally pushed forward by a series of small atomic explosions detonated behind it. On paper, this could cut the journey to a few centuries. In practice, no nation has ever tested it because of the obvious fallout problem and international treaties banning nuclear devices in space. There is one more option. A propulsion system that exists only as equations, requiring a substance so rare it costs more than gold dust scaled up by a factor no human economy can absorb. And this is where the dream begins to break. Every rocket that has ever flown shares the same brutal limitation. To go faster, you need more fuel, but more fuel means more weight. More weight means you need even more fuel to push that fuel. The harder you try to chase the stars, the more your own ship fights back. Engineers call this the tyranny of the rocket equation. It is the silent killer of nearly every interstellar dream ever sketched on a napkin. To picture the problem, imagine you are trying to drive a truck across the country. The truck gets 10 miles per gallon. Easy enough. But now imagine the gas station is also in the truck. Every gallon of fuel you carry adds weight, and that weight makes the truck consume more gallons just to move the gas itself. The farther you want to go, the more of your truck has to be fuel, until eventually there is no room for anything else. Not the driver, not the cargo, just gasoline. That is exactly what happens to interstellar rockets, except much worse. Chemical rockets, the kind we use to launch satellites and astronauts today, are pathetically inefficient for star travel. The fastest chemical exhaust speed is about 2.5 miles per second. To reach even 10% of light speed, a chemical rocket would have to be made almost entirely of fuel. With a fuel-to-payload ratio so absurd that the ship would need to be larger than every ocean liner ever built combined, and that is just to reach a fraction of the necessary velocity. Switching to nuclear fission improves things. Fission releases millions of times more energy per pound than chemical reactions. A nuclear-powered ship could reach Alpha Centauri in maybe a few thousand years. Better than Voyager, but still useless for any human mission. Fusion is the next dream. If we could harness the same reaction that powers our nearest star, exhaust velocities could climb high enough to reach a few percent of light speed. The trip might take only 100 years. The problem? After 70 years of research, controlled fusion still does not work as a practical engine. The closest experimental reactors barely break even on energy, and they are stadium-sized buildings nailed to the ground. Shrinking that into a starship is a leap nobody has been able to make. Beyond fusion lies antimatter. Antimatter is the most energy-dense fuel theoretically possible. When it touches normal matter, the two annihilate completely, converting their entire mass into pure energy. Pound for pound, antimatter is about 10 billion times more energetic than gasoline. A spaceship powered by antimatter could potentially reach Alpha Centauri in a single human lifetime. The math finally cooperates. The dream finally seems possible, except for one detail. Producing antimatter is currently the most expensive process humans have ever invented. Every particle accelerator on Earth combined produces less than 1/1000th of a gram of antimatter per year. To fuel a single starship would require a few pounds of the substance. At current production rates, it would take many trillions of years to make enough. The universe itself is only 14 billion years old. We would need to begin manufacturing now and continue past the death of every star ever born. And even if we somehow got the fuel, something terrifying happens to the ship the moment it starts moving fast enough. There is an equation that haunts every space engineer. It was first worked out by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903. He scribbled it down before airplanes had even crossed the English Channel, and his formula has tortured rocket scientists ever since. The equation is simple to state. The speed your rocket can reach depends on two things: how fast your exhaust shoots out the back, and how much of your rocket is fuel versus payload. The relationship between these numbers is not a gentle slope. It is a wall that gets steeper the harder you push. Want to double your final speed? You do not double your fuel, you square it. Want to triple your speed? You cube your fuel. The numbers explode upward in a way that makes every interstellar plan collapse under its own weight. Here is a real example. Suppose you want to send a small probe, about the size of a refrigerator, to Alpha Centauri at 10% of light speed. That would mean a journey of about 43 years, achievable in a human lifetime, in theory. If you tried to do this with the best chemical rockets ever built, the fuel mass required would be larger than the observable universe, larger than the universe. The numbers literally have no physical meaning. Switch to nuclear fusion, the thing that powers stars, and the fuel mass drops dramatically. But it is still ridiculous. You would need a fuel tank weighing more than every aircraft carrier, oil tanker, and skyscraper on Earth combined, just to send one refrigerator-sized box to the nearest star. The rocket equation does not care about your dreams. It does not care about how clever your engineers are. It is a piece of mathematics that simply tells you the truth, and the truth is brutal. Now flip the problem around. What if you do not care about getting there fast? What if you're willing to take 1,000 years? That helps a little. The fuel requirements drop by orders of magnitude, but now you have a different problem. Your spacecraft has to survive intact for 1,000 years. Every wire, every seal, every joint, every screw, every solar cell, all of them have to keep working through 10 centuries of cosmic radiation, micro-impacts, and thermal stress. Nothing humans have ever built has lasted that long while continuously functioning. The oldest still working machine on Earth is the Prague astronomical clock, and it has been repaired and rebuilt repeatedly since the 1400s. A spacecraft cannot be repaired in deep space. There is no mechanic between here and Alpha Centauri. Engineers have tried to soften the rocket equation with creative tricks. Multi-stage rockets dump empty fuel tanks as they go, which helps a bit. Solar sails skip the fuel problem entirely by riding light pressure, but they accelerate too slowly for serious interstellar speeds. Beam propulsion uses a giant laser back home to push the ship, but the laser would need to be the size of a small country. Every workaround introduces a new impossibility. Every solution births a fresh nightmare. The rocket equation always wins in the end, smiling quietly while engineers tear their hair out. But suppose, against all odds, you do build a ship that goes fast enough. The next horror is what space itself does to that ship the moment it starts hauling. Imagine a spacecraft finally reaches 20% of light speed. After centuries of failed dreams, engineers have somehow cracked the propulsion problem. The ship is humming through interstellar space, hurtling toward Alpha Centauri at 60,000 miles per second. That is not a typo. 60,000 miles every single second. At that velocity, the craft could circle the Earth 8 times in less than 3 seconds. Now picture the front of the ship, just a flat metal plate facing forward. Looks peaceful enough. Empty space ahead. Nothing visible, nothing solid. The vacuum of the cosmos is famously empty, except it is not empty. Interstellar space contains roughly 1 atom per cubic centimetre on average, mostly hydrogen, with traces of helium and a little dust. To anyone standing still, this is essentially nothing, less than the best laboratory vacuum ever achieved on Earth. You could wave your hand through that density of matter and never feel a thing. But the spacecraft is not standing still. It is ploughing forward at 20% of light speed. At that velocity, every single hydrogen atom in front of the ship slams into the hull with the energy of a high-powered rifle bullet. Not a gentle puff, not a soft drift, a bullet. Continuously, every microsecond, trillions upon trillions of them, hour after hour, year after year. The front of the ship is no longer a peaceful metal plate. It is being machine-gunned by the universe itself. The physics gets worse. When a hydrogen atom hits the hull at relativistic speed, it does not just bounce off, it penetrates the metal. It slams into the atoms inside the ship. It releases a burst of high-energy radiation, including X-rays and gamma rays, deep inside whatever shielding you tried to install. The hull does not just erode from the outside, it glows from within. Calculations done by physicists suggest that even a few centimeters of ordinary metal would be vaporized within months at these speeds. The ship would essentially be sandblasted out of existence by atoms it could not even see. And atoms are the small problem. Interstellar space also contains dust grains, tiny specks. A typical interstellar dust particle is about 1 micrometer across, smaller than a human red blood cell. Microscopic, invisible, harmless under normal circumstances. A single dust grain hitting the ship at 20% of light speed releases the energy of a hand grenade. 1 grain, 1 grenade, embedded directly into the front of your spacecraft. Bigger grains release the energy of artillery shells. The largest interstellar particles, which are still smaller than a pea, would deliver impacts equivalent to small nuclear devices. Now consider that across 4 light years, the spacecraft will encounter an unknown number of these grains. The path is not mapped. There is no way to scan ahead and dodge them. The dust is too small to detect from Earth. The ship would only know it was hit when chunks of itself started peeling away. Engineers have proposed solutions. A sacrificial shield made of layered ice or beryllium might absorb some of the damage. A magnetic deflector could push charged particles aside before they hit. Each idea adds enormous mass, which then breaks the rocket equation all over again. The math is unforgiving. But there is something even more disturbing waiting for the crew inside the ship. Most people picture deep space as perfectly clean. a black silent emptiness with nothing in it but stars. That picture is comforting and completely wrong. The space between stars is filled with thin clouds of dust, gas, and ice particles, drifting along on currents of ancient stellar winds. These clouds are sparse, so sparse that you could fly a regular airplane through one and never notice. The density of interstellar dust is about one tiny grain in every cubic mile of space. From a human perspective, that is essentially zero. But for a starship moving at relativistic speed, that zero becomes a death trap. Here is where the math turns ugly. A typical interstellar dust grain weighs about 100 trillionth of a gram. Vanishingly small, smaller than the dust on your bookshelf by orders of magnitude. You could sweep up 1 billion of them and not feel any weight in your hand. Yet kinetic energy depends on velocity squared. The faster something moves, the more disproportionately violent its impact becomes. At 10% of light speed, a single one of these microscopic grains carries the punch of a rifle round. At 20%, it acts like a hand grenade. At 50%, it becomes a small bomb. Now spread that across a 4-year journey. The ship will plough through trillions of dust grains. Not all of them are tiny. The interstellar medium contains a smooth distribution of particle sizes, from nanometer specks all the way up to occasional grains the size of sand. A sand grain hit at relativistic velocity would leave a crater the size of a swimming pool in any practical hull material. The crew, if there is one, would never see the grain coming. There is no warning system. The grains are too small to image from Earth. They are too small to detect with onboard radar until they are already inside the ship. Engineers have sketched defensive ideas. The most popular concept is called a Whipple shield, named after Fred Whipple, the astronomer who first proposed it for protecting craft from micrometeoroids. A Whipple shield is essentially a thin sacrificial layer placed several feet in front of the main hull. When a grain hits the outer layer, it vaporizes into a cloud of plasma. By the time that cloud reaches the inner hull, it has spread out enough to do less damage. This works wonderfully at low orbital speeds. At interstellar velocities, the Whipple shield itself gets vaporized within hours. The plasma cloud it produces is so energetic that it punches through the inner hull anyway. The shield has to be replaced or rebuilt mid-flight, which is impossible in deep space. Other concepts involve a giant ice block placed at the front of the ship. Ice is cheap, easy to manufacture in space, and it absorbs impacts well. A starship with a 10-meter thick ice cap on its nose could survive longer. But the ice slowly evaporates from cosmic radiation and impact heat, meaning the cap shrinks during the trip. Calculations show the ice would be completely gone before reaching Alpha Centauri. A magnetic shield could deflect charged particles, but neutral dust grains are immune to magnetic forces. They sail right through and hit the hull anyway. Every defense leaks. Every solution fails. The ship slowly disintegrates as it travels, even before it arrives at any destination. And while the hull is being chewed apart from the outside, an even more invisible enemy is cooking everything inside. Earth wraps its inhabitants in 2 protective blankets. The atmosphere absorbs most harmful radiation from space. The planet's magnetic field deflects charged particles away from the surface. Together, these shields keep the radiation dose at the ground level safe for biology to develop and survive. Step outside that protection, and the universe stops being friendly. The space between stars is flooded with cosmic rays. These are not actual rays of light. They are atomic nuclei, mostly protons, that have been accelerated to nearly light speed by violent events like supernova explosions and active black holes. They scream through the galaxy in every direction, a constant background radiation that has been streaming for billions of years. On Earth, you receive a tiny dose of cosmic rays every day. Most are stopped high in the atmosphere. The few that reach you are insignificant. You would have to fly in an airplane for many years before noticing any effect. Astronauts on the International Space Station are different. They orbit just above the densest layers of atmosphere, so they get a much higher dose. 6 months on the station delivers roughly the radiation equivalent of a few thousand chest X-rays. Manageable, but noticeable. A trip to Mars would be substantially worse. NASA studies estimate that a round-trip Mars mission would deliver about 1 sievert of radiation to each crew member. That is enough to increase cancer risk by a measurable amount, and is approaching the lifetime exposure limit for radiation workers. Now multiply that by a journey to Alpha Centauri. A century-long voyage outside the protection of any star system would deliver a radiation dose hundreds of times higher than anything any astronaut has ever endured. Without massive shielding, the crew would be effectively dead within months. their bone marrow would fail, their immune systems would collapse, the cells lining their stomachs would slough off, every organ would be assaulted simultaneously. Cosmic ray particles do something especially nasty. When a high-energy proton hits a cell, it does not just damage one strand of DNA. It often punches through dozens of cells in a row, leaving a streak of destruction along its path. The body cannot easily repair this kind of damage because it is too concentrated and too widespread at the same time. Shielding helps, but the kind needed for interstellar travel is staggering. To reduce cosmic radiation to safe levels, the crew compartment would need to be wrapped in roughly 6 feet of water or 15 feet of polyethylene. The mass penalty is enormous. A cylinder of water thick enough to protect a small crew cabin would weigh hundreds of tons. Add all that mass to the ship, and the rocket equation strikes again. More shielding means more weight, which means more fuel, which means more weight in an endless loop. Some designs propose using the spacecraft's own fuel as shielding. Hydrogen fuel can absorb cosmic radiation effectively, so the fuel tanks are placed around the crew compartment. This works while the tanks are full. Halfway through the journey, the shielding has burned away in the engines and the crew is exposed for the rest of the trip. There are also secondary radiation effects. When cosmic rays slam into the hull, they create showers of secondary particles, like the breaking of one rock into many. Some shielding designs actually make the radiation problem worse, not better, because they generate these showers right next to the crew. Even if you somehow protect the bodies of the travellers, their minds face a different kind of pressure that no shield can block. Suppose engineers solve every technical problem. The fuel works, the ship survives, the radiation is blocked, the dust is deflected, everything functions perfectly. The voyage will only take 100 years. Now comes the part nobody wants to think about. Who actually goes? A century is longer than any human life. Even with the best modern medicine, no person born today will be alive in 100 years, which means the people who launch will not be the people who arrive. The mission has to be a generation ship, where the crew members are the great-grandparents of whoever steps off at the destination. This idea sounds romantic in science fiction novels. In reality, it is a logistical and ethical nightmare. First, the practical math. A self-sustaining crew needs a minimum genetic diversity to avoid inbreeding collapse. Population biologists have run the numbers. A multi-generational crew needs at least 160 genetically unrelated people to safely reproduce for centuries without serious genetic damage. Some studies push the number above 500 to be truly safe. 500 people, each one needing food, water, oxygen, clothing, medical care, and living space for 100 years. The required cargo mass climbs into the millions of tons. The ship is no longer a vehicle. It is a small floating city that has to manufacture its own everything. Now multiply the food problem. A single human eats around a ton of food per year. 500 humans across a century need roughly 50,000 tons of food, or the ability to grow it on board. Closed-loop ecosystems that can produce food, recycle waste, and maintain themselves for 10 generations have never been successfully built on Earth, even in controlled experiments. The famous Biosphere 2 project failed within 2 years, suffocating from oxygen drops and crop collapses. Then the human problem. Children born on the ship will never have chosen to be there. They are not volunteers, they are not explorers, they are people imprisoned inside metal walls because of decisions their ancestors made before they were born. They will live and die without ever feeling sunlight on grass. They will never swim in an ocean. They will never see a horizon. Many ethicists have pointed out that this raises a serious moral question. Is it acceptable to condemn unborn generations to a sealed life inside a tin can in the dark? Even if the destination is glorious, the people in the middle of the journey will live their entire existence inside corridors that smell like recycled air. Add psychological collapse. History shows that small isolated communities tend to fracture. Religious cults split. Antarctic research stations report depression rates above 50%. Even short submarine deployments produce serious mental health issues. Now stretch that across 100 years with no escape, no rescue, no break. The crew might also lose connection with their mission. Why would the great-great-grandchildren of the original launch team feel any duty to keep going? They might decide to turn around. They might decide to attack each other. They might forget the science needed to operate the ship. By Generation 4, the engineers who built the systems would all be dead, and the new generation might not understand the machines they live inside. Some thinkers have proposed a darker solution. Skip the generations entirely by freezing the crew before launch. Wake them up at the destination. no descendants, no drama, just sleeping bodies arriving fresh. But that solution opens its own coffin lid of horrors. The idea sounds elegant. Freeze the crew at launch, send them sleeping through the dark, thaw them out when the ship reaches Alpha Centauri. No food required, no oxygen consumed, no drama, no generations of trapped descendants, just sleeping bodies arriving fresh on a new world. Science fiction has loved this concept for almost a century. Cryogenic sleep, suspended animation, hibernation pods. They appear in countless films and novels because they conveniently solve every problem of long-duration space travel in a single stroke. There is one minor issue: it does not work. Despite decades of research, no human has ever been successfully frozen and revived. Not one. The reason is biology. When water inside cells freezes, it forms sharp ice crystals that puncture cell membranes from the inside. Every cell in the body suffers this damage simultaneously. By the time the body's fully frozen, every tissue is shredded at the microscopic level. You can cool a human down very slowly and partially circumvent this. Hospitals do something called therapeutic hypothermia, lowering a patient's body temperature to about 90 degrees Fahrenheit during certain surgeries. It buys time during cardiac arrest. But anything below about 68 degrees causes irreversible organ damage in humans. To truly halt all biological activity, the body has to be cooled to near absolute zero. That is roughly negative 400 degrees Fahrenheit. At those temperatures, every fluid in the body freezes solid. The damage from ice crystals is catastrophic and total. Some companies advertise cryogenic preservation services. They claim to freeze human bodies after legal death and store them indefinitely, hoping future medicine will revive them. None of these patients have ever been brought back. Most scientists in the field are skeptical that any of them ever will be. The cellular damage may simply be irreversible by any conceivable technology. Cryoprotectants are chemicals that replace some of the water in tissues to reduce ice crystal formation. They work for individual organs in lab experiments. Researchers have successfully frozen and revived isolated rabbit kidneys. Whole-body cryoprotection has never worked. The chemicals are toxic at the concentrations needed, and they cannot reach every tissue evenly. Some animals do hibernate naturally. Arctic ground squirrels can drop their body temperature below freezing during winter sleep. Wood frogs can survive being partially frozen solid. Tardigrades, those microscopic water bears, can survive years of complete dehydration and the vacuum of space. Humans have none of these adaptations. Our biology was tuned by evolution for warm weather and constant metabolism. Switching off a human and switching them back on is not something nature ever intended. Even if cryogenic sleep worked perfectly, there is still the technology question. The freezing pods would have to maintain perfect conditions for 100 years without any maintenance. Power must never fail. Coolant must never leak. The seals must never crack. A century of flawless operation in deep space, with no mechanic, no backup parts, and no second chances. Imagine arriving at Alpha Centauri after a century of sleep. The pod opens. The system reports successful revival. You sit up blinking, ready to begin a new chapter of human history. Then you realize the pod next to yours failed silently 50 years ago. And the pod next to that one, and every other pod. You're the only survivor of a crew of 500, alone in another star system, with nothing to come home to. If freezing fails, what about staying awake but going mad? Humans evolved on a busy planet. Our ancestors lived in groups of 20 to 50 people, surrounded by changing landscapes, weather, animals, and seasons. Every sense was constantly stimulated. Every day brought something new. Take that human and seal them inside a metal tube for 100 years. Same walls, same recycled air, same faces, same hum of the same machines. The brain does not respond well. We already have data on what happens to humans in extended isolation. Antarctic research stations are the closest analogue. Crews of scientists spend 6 months to a year locked inside small bases during the polar winter, unable to leave because of sub-zero temperatures and constant darkness. Studies of these crews show alarming patterns. Within months, sleep cycles fall apart, memory becomes fuzzy, decision-making degrades. Roughly 1/3 of overwinter crews develop measurable depression. A smaller but significant fraction develop something researchers call winter over syndrome, which includes irritability, hostility, and what some have described as a kind of waking dream state. Submarine crews show similar patterns on shorter timescales. Even highly trained military personnel begin showing signs of psychological strain after a few months underwater. The Russian Mir space station hosted cosmonauts for missions of up to 14 months. Returning crew members reported memory gaps, emotional flatness, and difficulty readjusting to life on Earth. Now stretch that across 100 years, or even 300 years for slower ship designs. The crew is locked inside a vessel smaller than a city block, looking at the same companions for their entire lifespan. There is no horizon to gaze at. There is no weather. There are no birds, no wind, no rain. The walls are always the walls. Studies have suggested that prolonged isolation in monotonous environments can cause hallucinations even in mentally healthy people. The brain craves stimulation. When deprived, it begins manufacturing its own. Sailors lost at sea have reported phantom companions. Solitary confinement in prisons produces similar effects within weeks. Now imagine what happens after years, decades, generations. Conflict becomes almost inevitable. With nowhere to go, every disagreement festers. A quarrel over food preferences in week 1 becomes a feud by year 5 and a faction war by year 50. The Mars Analog Mission. Mars 500, where 6 volunteers were locked in a simulated spacecraft for a year and a half, reported significant interpersonal tensions, even in a carefully selected, well-trained group of professionals on Earth. Religion and ideology might shift dramatically. Sealed communities tend to develop their own beliefs, language, and customs over generations. By the time the ship arrives at Alpha Centauri, the crew might no longer share any cultural connection with the people who launched them. They might worship different gods, speak different versions of English, follow rules invented by their grandparents that no one back on Earth ever heard of. Mental health treatment options would be limited. There is no psychiatrist down the hall. The ship's medical officer, if there is one, might themselves be struggling. Antidepressants would have a finite shelf life and could not be manufactured indefinitely on board. Some designs propose using virtual reality to ease the strain. Crew members could escape into simulated forests and oceans whenever they need a break. That helps for short stretches. Studies show people quickly recognize the artificiality, and the relief diminishes over time. The mind always knows when it is being lied to. Even if the crew survives mentally and physically, their connection to home faces a different kind of break. Light is the universal speed limit. Nothing travels faster, including radio waves, which are simply low-energy light. When you call someone on a phone, the signal moves at light speed. Across a city, this is instantaneous. Across a country, you might notice a brief lag on a satellite call. Across the gulf between stars, light becomes painfully slow. Alpha Centauri is roughly 4.3 light-years away. That phrase contains a simple, devastating fact. A radio message sent from Earth takes 4.3 years to arrive there. The reply, if anyone is listening, takes another 4.3 years to come back. Every conversation between Earth and a starship at Alpha Centauri would have a round-trip delay of about 8.5 years. Imagine asking the ship a question. Maybe you're a mission control engineer in 2050, and you radio the crew about a system problem. You sip your coffee, you wait. You wait until 2058 to hear the answer. By then, the engineer who asked the question may have retired or died. The system being asked about may have failed completely. The answer arrives long after it could have helped anyone. This is not a small inconvenience. It fundamentally breaks every assumption mission control has ever made about how to support a crewed spacecraft. Apollo astronauts could call Houston for advice in real time. The Mars rover Curiosity has a delay of about 20 minutes one way, which is annoying but workable. A Mars crew of the future would have a 40-minute round trip, manageable for non-urgent communication. A Starship crew has more than 8 years of round-trip lag. They are completely on their own. There is no support. There is no second opinion. There is no Houston to call when something breaks. The ship has to be entirely self-sufficient for every decision. The crew must be able to handle every emergency, every medical issue, every system failure, every interpersonal crisis, without any external help. They must also accept that any message they send home is essentially a goodbye letter. The reply will come, but they cannot have a real conversation. Now consider news. The crew leaves Earth in some particular year. They will receive radio updates about events back home, but always 4 years late. By the time they hear about a major political event, the world has already moved on. By the time they react, another 5 years has passed before their reaction reaches Earth. Earth and the ship effectively become two separate civilizations. drifting apart culturally as well as physically. The ship's library of human knowledge becomes frozen at the moment of launch. New songs, new books, new films, new scientific discoveries trickle in years late, and the crew can never participate in any of them in real time. There is also a brutal practical issue. The signal from Earth must be powerful enough to reach the ship. Across 4 light years, even the largest radio dishes on Earth would need enormous power to transmit a usable signal. The ship's antenna would need to be precisely aimed back at Earth, which is just a moving point of light from that distance. Any error in pointing means the signal misses entirely. Some missions might solve part of this with onboard artificial intelligence advisors that can simulate ground support locally. The crew talks to a machine instead of a human back home. But this ties the entire mission's wisdom to whatever software was loaded at launch, with no real-time updates possible. Despite all these obstacles, one bold plan promises to bypass the entire crew problem, and it might actually work. In April 2016, a group of scientists and billionaires gathered in New York to announce something extraordinary. The project was called Breakthrough Starshot, and it claimed to have a real plan for reaching Alpha Centauri within a single human generation. The lead figures were physicist Stephen Hawking, technology investor Yuri Milner, and Facebook founder Mark Zuckerberg. They committed $100 million to research the concept. The goal was to send a probe to our nearest stellar neighbours and get pictures back within 40 years. Everyone assumed this was impossible. Starshot proposed a stunning workaround. Forget building a giant spaceship, forget freezing crews, forget generation ships. Instead, build something the size of a postage stamp. A tiny silicon wafer carrying cameras, communication gear, and a small computer, weighing only a few grams total. Call it a nanocraft. Attach this nanocraft to a sail made of impossibly thin reflective material, just a few atoms thick across an area of about 13 feet on each side. Then build an enormous array of lasers on Earth. Aim the lasers at the sail. Fire. The light from the lasers pushes the sail. Because the sail is so light, the acceleration is staggering. In just a few minutes, the nanocraft would be travelling at 20% of light speed. At that velocity, it could reach Alpha Centauri in about 20 years. Add another 4 years for the radio signal to come back to Earth, and you get a round trip of about 24 years. A teenager born today could be in their 40s when the first images arrive from another star, within a single career, within a single lifetime. The plan elegantly sidesteps almost every problem that has crushed previous interstellar dreams. No fuel is carried on board, so the rocket equation is bypassed. No crew is sent, so radiation, food, and psychology stop mattering. The probe is small enough that even some impacts can be tolerated, since hundreds or thousands of these wafers can be launched as a swarm. It sounds beautiful. Many physicists have called it the first plausible interstellar mission concept ever proposed. But Starshot has a hidden flaw, and it is enormous. The laser array required is unprecedented. To accelerate a single nanocraft to 20% of light speed, the array must deliver about 100 gigawatts of focused power. That is more electricity than every power plant in Belgium produces, all aimed at a target the size of a dinner table from Earth. The total energy needed for one launch equals about a year of electricity use for a small nation, and the laser must remain perfectly stable, perfectly focused, for the entire 10-minute boost phase. If the beam wobbles even slightly, the sail tears or burns up. The engineering challenge is closer to building a small star on the ground than to building a normal facility. The cost estimates run into the tens of billions of dollars just for the laser. No nation has yet committed to building it. There is a second flaw. The probe arrives at Alpha Centauri at 20% of light speed and just keeps going. There's no way to slow it down. It blasts through the system in a few hours, snapping photos as it flies past and then heads off into deep space forever. A flyby is not the same as exploration, and the probes have one more problem nobody likes to mention. The laser array proposed by Breakthrough Starshot is, on paper, the most ambitious construction project ever conceived by humans. To understand how much energy it actually requires, it helps to put the numbers in real-world terms: 100 gigawatts. That is the peak power needed to push a single nanocraft to interstellar speed. For a few minutes of operation, the array must produce more energy than every nuclear power plant in the United States combined. Where does that power come from? The current largest single laser facility on Earth is the National Ignition Facility in California. It uses 192 giant lasers to compress a tiny pellet of fuel for fusion experiments. When all of them fire together for a fraction of a second, they deliver about 500 trillion watts. Sounds enormous. That facility fills a building the size of a sports stadium and costs over $3 billion. And it produces a single pulse lasting a few billionths of a second. Sustained operation is impossible. The facility takes hours to recharge between shots. The Starshot array would need to deliver a continuous beam at far higher power for 10 minutes straight, then maintain accuracy across 13 million miles of distance during that entire time, since the nanocraft is racing away faster than the laser pulse can catch up. The laser beam must remain focused on a target the size of a card table from Earth's surface, with the atmosphere distorting the beam, with Earth's rotation moving the array, with the target getting farther away every microsecond. The optical engineering required is decades beyond anything humans have ever built. Even the best modern telescopes struggle to maintain pointing accuracy across much smaller distances. The Starshot array would have to be at least an order of magnitude better. Then there is the energy supply. A continuous output of 100 gigawatts requires either a massive grid connection or a dedicated power station. Most plans propose building a giant battery bank, slowly charged over weeks, that releases its stored energy in a single 10-minute burst. The battery itself would be one of the largest energy storage facilities ever constructed. Starshot supporters argue that the technology will improve. Lasers are getting more efficient every year. Solar power is dropping in cost. Battery technology is advancing. By the year 2040 or 2050, perhaps the array becomes affordable. Skeptics counter that the physics has hard limits. There is a minimum amount of energy required to push a sail to relativistic velocity. That minimum cannot be reduced by clever engineering. The basic budget is set by the laws of motion. There is another hidden problem. The atmosphere blocks and distorts laser light. Building the array on the ground means losing efficiency to air absorption, weather interference, and atmospheric turbulence. Some proposals call for building the array on the Moon, where there is no atmosphere. But constructing a multi-billion-dollar facility on the lunar surface is a project even bigger than building a space station. A smaller version on Earth might work for a slower probe. A 2% light speed probe could be launched with maybe 10 gigawatts. The trip would take 200 years instead of 20. Still useful, but no longer fits into a human lifetime, and no matter how clever the laser, the probe still cannot stop when it arrives. There is a strange truth about interstellar travel that most people never consider. The hardest part of the journey is not getting up to speed. It is getting back down. Imagine driving a car from one city to another. Speeding up is easy. Press the gas pedal, wait. The car accelerates smoothly. Now reaching your destination, you need to stop. You press the brake. The car slows down. Simple. In space, there is no road. There is no friction. There is no air resistance. There is nothing to push against. A spacecraft moving at 20% of light speed will keep moving at 20% of light speed forever, unless something actively pushes it backward. Pushing it backward requires the same amount of fuel that was used to speed it up in the first place. This is the dirty secret of every interstellar plan that involves slowing down. You need a second engine, with a second tank of fuel equal to the first. The mission has to carry its own brakes, and the brakes have to fire in the opposite direction at the destination. For a chemical rocket, this doubles the fuel requirement, which by the rocket equation actually means it quadruples, or worse, the total fuel mass, because you have to carry the deceleration fuel along with you the whole way. For Starshot, the deceleration problem is even worse. The original plan has no engine on board. The nanocraft is pushed by the laser at Earth, accelerated to 20% of light speed, and then coasts forever. There is no laser at Alpha Centauri to push the probe in the opposite direction. This means the nanocraft will not stop at Alpha Centauri. It will not enter orbit around any planet. It will not land. It will not even slow down to take detailed measurements. It will scream through the entire star system in a few hours, snapping rapid-fire photos as it passes, and then continue out the other side and head into deep interstellar space forever. Some scientists have proposed creative solutions. One idea is to use the gravity and stellar wind of Alpha Centauri itself to slow the probe down. As the nanocraft enters the star system, the radiation pressure from the 3 Centauri stars pushes against the sail in reverse, gradually decelerating it. Calculations suggest this could slow a sail probe enough to enter orbit, but only if the sail is unfurled at exactly the right moment and the geometry of the encounter is perfect. Another idea is to send a series of probes in a chain. Each probe carries fuel for the next one. The chain stretches across light years, with later probes refueling earlier ones during their journey. The logistics are absurd, but the physics works. A third idea uses what is called a magnetic sail. The probe deploys a giant loop of superconducting wire that interacts with the interstellar plasma like a parachute. As the probe rams into the gas of the destination system, the magnetic loop creates drag and slows it down. This concept exists only on paper and requires materials that have not yet been invented. For a crewed mission, deceleration is non-negotiable. You cannot ask astronauts to fly past their destination at 20% of light speed and just wave at the planet as they go by. They have to stop. They have to land, which means they need brakes that work, and brakes are heavy. Brakes are expensive. Brakes are exactly the thing the rocket equation hates most. Even if the ship somehow stops, what awaits the crew might be far less inviting than expected. Suppose the propulsion is solved, the shielding works, the crew is somehow stable, everything functions. Now zoom into the daily life on board. Look at what each crew member needs simply to stay alive each day. A human eats about 4 pounds of food per day. A human drinks about 3 quarts of water. A human breathes about 2 pounds of oxygen. Multiply all of that by 365 days. Multiply that by 100 years. Multiply that by 500 crew members. The numbers explode into the millions of tons. Carrying that much cargo is impossible by every known propulsion method. The ship would weigh more than the largest battleships ever built just for groceries, which means the ship cannot carry food. It must grow food. It must produce its own water. It must generate its own oxygen. It must do this continuously for 100 years without external resupply. This is called a closed ecological life support system, and humans have never built one that works. The most famous attempt was Biosphere 2, a domed greenhouse complex in Arizona. 8 people sealed themselves inside for 2 years in 1991, trying to live entirely off the plants and animals contained in the structure. The experiment failed in multiple spectacular ways. Oxygen levels dropped because concrete in the walls was secretly absorbing it. Crop yields collapsed because of unexpected pest cycles. Insect populations exploded out of control. The crew lost significant weight from malnutrition. By the end, the team was barely speaking to each other. They had to pump in fresh oxygen from outside to keep everyone alive. The closed system was not actually closed. It was leaking and starving. That experiment lasted 2 years on Earth, with sunlight, gravity, mild temperatures, and the option of emergency rescue. Imagine extending it to 100 years, in zero gravity surrounded by deadly vacuum with no rescue possible. Hydroponics and aeroponics offer some hope. These are methods of growing plants without soil, using nutrient-rich water or mist instead. They are efficient and can produce food in small spaces, but they require constant attention, complex pumps and filters, and energy for artificial lighting that simulates sunlight. A starship growing food this way would need to be partly farm. Acres of crops under artificial lights, consuming megawatts of power, tended around the clock by crew members who become as much farmer as astronaut. Then there is the question of variety. Humans cannot survive on potatoes alone forever. The crew needs proteins, vitamins, healthy fats, fibre, and 100 other compounds. Producing all of these in a closed ecosystem requires plants, fungi, perhaps insects or fish, all interacting in delicate balance. One missing nutrient over years leads to health collapse. Recycling is also a nightmare. Human waste must be processed back into usable nutrients. Carbon dioxide from breathing must be converted back into oxygen, usually by plants. Water must be purified from sweat, urine, and humidity, then redistributed. Every gram of every element must cycle through the system without loss, because there is no way to add new material from outside. A single broken pump could doom the mission. A single crop disease could starve the crew. A single air filter failure could suffocate everyone in their sleep. Backup systems help, but backups also fail over decades. Spare parts run out. Repair skills are forgotten. By Generation 3, the descendants might not even understand the machines they depend on. Even if every system works perfectly, the destination itself might not be the paradise that astronomers once promised. In August 2016, astronomers announced one of the most exciting discoveries in modern science. A planet had been found orbiting Proxima Centauri, the closest star to Earth. The planet was named Proxima b. It was roughly Earth-sized. It orbited inside the habitable zone where liquid water could exist on the surface. The headlines wrote themselves: a second Earth right next door, a nearby world that might harbour life, a potential destination for humanity's first interstellar mission. For a few weeks it seemed like the universe was finally cooperating. Of all the stars in the sky, the closest one happened to have a planet that might be habitable. What were the odds? It felt like fate. Then the follow-up studies arrived, and the dream began to wilt. Proxima b orbits its host star at a distance of only about 4.6 million miles. For comparison, our planet orbits its star at 93 million miles. That seems like a problem. Surely a planet that closed should be roasted alive. It is not, because Proxima Centauri is a red dwarf. These small, dim stars produce only a fraction of the energy that our home star produces. So even though Proxima b is much closer to its star, it receives roughly the same amount of light and heat that Earth does. On paper, this works. In practice, red dwarfs are violent. They are notorious for producing enormous flares, sudden bursts of radiation hundreds of times more powerful than anything our local star ever emits. Proxima Centauri is one of the more active red dwarfs known. It throws out huge flares regularly, and at least one observed flare in 2019 was the most powerful ever recorded from any star. A planet orbiting that close to such an angry star would be hammered by these flares constantly. Each flare blasts the planet with deadly ultraviolet and X-ray radiation. Each flare strips away parts of the planet's atmosphere. Over billions of years, this gradual erosion likely removes most of the protective atmospheric layer, leaving the surface exposed to lethal radiation levels. The atmosphere is the first thing life needs. Without it, water boils away into space. Without it, the surface is sterilized. Without it, the planet looks more like our airless moon than like Earth. The next problem is the orbit itself. Proxima b takes only about 11 days to complete one trip around its star. 11 days. That is its entire year. Such tight orbits almost always result in something called tidal locking, where the same side of the planet always faces its star. Half of Proxima b is therefore in eternal daylight. The other half is in eternal night. The day side is baked. The night side is frozen. The temperature difference between hemispheres could be hundreds of degrees, generating violent winds at the boundary between light and dark. Some scientists argue that a thick atmosphere could redistribute heat enough to make the planet habitable. The flares might not have stripped everything away. The night side might be warm enough for liquid water if the air carries heat from the day side. These are all maybes. The truth is nobody knows yet what Proxima b actually looks like. We have no images. We have no spectra of its atmosphere. We only know it exists because it makes its star wobble slightly. Imagine travelling for 100 years to reach a planet only to discover it is a flare-blasted, tidally locked atmosphere-stripped rock. The crew arrives, the cameras turn on. The disappointment would be measured in lifetimes. And the host star is only the first of 3 problems waiting in that system. Red dwarfs make up about 3/4 of all stars in the galaxy. They are the most common type of star by far. They burn cool and slow, lasting trillions of years compared to the relatively short lifespans of larger stars. For a long time, astronomers assumed that planets around red dwarfs would be the most likely places to find life, simply because there are so many of these stars. That hope is fading fast. Red dwarfs have a dirty secret. Despite their small size, they are some of the most violent stars in the galaxy. They produce flares so intense that they can outshine the rest of the star's normal output for minutes at a time. These flares hurl massive amounts of charged particles, ultraviolet radiation, and X-rays into surrounding space. Proxima Centauri, the host of the planet Proxima b, is a textbook example. In March 2016, astronomers caught it producing a flare so bright that the star briefly became visible to the naked eye from Earth. For comparison, Proxima Centauri is normally far too dim to see without a telescope. A larger flare in May 2019 was even more dramatic. The star's brightness in ultraviolet light increased by a factor of 14,000 within seconds. 14,000 times brighter. Then it faded. Then another flare came along months later, and another. Now imagine you are standing on the surface of Proxima b when one of these flares hits. The sky suddenly explodes in light. The temperature spikes. Ultraviolet radiation floods the atmosphere. Any unprotected biology on the surface would be cooked alive within minutes. That is bad enough for life. The bigger problem is what flares do to atmospheres over geological time. When a flare hits a planet, the high-energy particles strip away gas molecules from the upper atmosphere. Oxygen, nitrogen, water vapour all blasted into space, never to return. A single flare removes only a tiny fraction. But across billions of years and millions of flares, the atmosphere slowly bleeds away. Earth has a strong magnetic field that deflects most of these charged particles before they can reach the atmosphere. We also have an atmosphere thick enough that small losses do not matter much. We are protected by both a shield and a thick coat. Planets close to red dwarfs probably have neither. Their tight orbits put them inside what scientists call the Alpha Centauri surface, a region where the star's magnetic field still grips the surrounding plasma. This means the planets are constantly being lashed by the star's wind and field even between flares. Recent studies suggest that any planet orbiting in the habitable zone of a red dwarf likely loses its atmosphere within a few 100 million years, sometimes much faster. By the time we arrive, the surface might be a barren, airless rock similar to our own moon. There may be exceptions. If a planet started with an enormous water reservoir, like a deep global ocean, some of that water could constantly replenish atmospheric gases. If the planet has a strong magnetic field of its own, it could retain more of its air. If the host star calmed down significantly after its violent youth, the atmosphere might survive. These are big ifs. Astronomers are still arguing about which red dwarf planets, if any, could be truly habitable. Many now consider the entire class of red dwarf worlds questionable for life. For Proxima b specifically, the situation looks bleak. Its star is still very active. Its orbit is very tight. Its atmosphere has had 4 billion years of constant flaring to wear it down. There is one more issue with this kind of orbit, and it twists the planet itself into an impossible shape. Picture a planet that always shows the same face to its star. One side bakes in eternal daylight, the other side is locked in permanent night. There are no sunrises, there are no sunsets, there is no day-night cycle at all. Time simply stops moving across the sky. This bizarre arrangement is called tidal locking, and it is the likely fate of every planet orbiting close to a red dwarf, including Proxima b. To understand how this happens, look at our own moon. The moon is tidally locked to Earth. We always see the same face of it, which is why the backside was a mystery until spacecraft photographed it in 1959. The moon's gravitational pull on Earth created tides that, over billions of years, slowed the moon's rotation until one side permanently faced us. The same thing happens to planets that orbit very close to their stars. The gravitational pull of the star creates internal stresses that gradually lock the planet's rotation to its orbital period. After enough time, one hemisphere is in permanent daylight and the other in permanent darkness. For Proxima b, the orbital period is about 11 Earth days. That means the planet either rotates once every 11 days, slowly cycling its surface in and out of light, or, more likely, it does not rotate at all relative to its star. Now think about what this means for the planet itself. The day side is always hot. The night side is always cold. With no atmosphere to speak of, the temperature difference between hemispheres could be hundreds of degrees. The day side might reach temperatures that would melt lead. The night side might be cold enough to freeze nitrogen. Right at the boundary between day and night, called the terminator zone, conditions might briefly be moderate. This narrow band of permanent twilight is where life, if any exists, would have its best chance. Imagine a thin ring around the entire planet, maybe a few 100 miles wide, where the temperature is barely tolerable. Everything inside it lives in perpetual sunset. If the planet has any atmosphere, it would behave bizarrely. Hot air on the day side rises and rushes toward the night side. Cold air on the night side sinks and rushes back. The result is constant, hurricane-force winds blowing across the terminator zone, day after day, year after year, forever. Any liquid water would also behave strangely. On the day side, oceans would boil away into the atmosphere. On the night side, water would freeze into permanent ice sheets that never melt. If the atmosphere can carry water vapor across the terminator, the planet might develop a kind of permanent storm cycle, with rain on one side and snow on the other. This is not impossible for life. Some scientists argue that the terminator zone of a tidally locked planet might be one of the most stable habitats in the universe. Conditions there never change. Once life adapts to the constant twilight, it might thrive for billions of years without disruption. But it is not Earth. It is not what science fiction promised. It is not the lush green planet under a yellow sun that humans have always pictured when they imagined exoplanets. A crew arriving at Proxima b would step onto a world where the sun never moves, where one side is too hot to touch and the other too cold to walk across, where the only livable region is a narrow band of permanent storms and twilight, scoured by winds and bathed in red light from a flaring star. And the next problem comes from the other two stars in the system, the bigger ones, whose presence makes everything stranger. Most people think of Alpha Centauri as a single bright dot. Through a telescope, that dot splits into two stars. Alpha Centauri A and Alpha Centauri B are a binary pair, locked in a slow gravitational waltz. They orbit each other every 80 years. A third companion, Proxima Centauri, drifts at the edge of the system, more than 13,000 astronomical units from the main pair. Some astronomers debate whether Proxima is truly bound to the others or just passing through. Either way, the central drama is between the two big stars. This binary nature is great for telescopes. Astronomers can study two nearby stars in one trip. It is terrible for planets. Binary star systems are notoriously hard places for stable orbits. The gravity of two stars constantly tugs on any planet trying to maintain a regular path. There are only certain orbital regions where a planet can stay put long term. Outside those zones, the planet gets thrown out of the system entirely or sucked into one of the stars. Around Alpha Centauri A, the stable zone for planets extends out to about 3 astronomical units. Beyond that, the gravity from B disrupts everything. Around Alpha Centauri B, the stable zone is similar. Together, the two stars carve out a gravitational war zone where most orbits are simply impossible. Worse, the stable zones happen to overlap with the habitable zones in unfortunate ways. A planet in the right orbit to receive the right amount of heat from Alpha Centauri A would also be close to the chaotic edge of the gravitational stable zone. Any small disturbance could send the planet on a wild ride. For decades, astronomers searched for planets in this system. They found nothing for a long time. Some claim detections turned out to be false alarms, signal artifacts in the data rather than real worlds. Then in 2012, a team announced a planet around Alpha Centauri B. The world was given a tentative designation. It was Earth-sized. It was supposedly orbiting very close to its star. The headlines exploded. Other astronomers pored over the data, and the detection eventually fell apart. The signal turned out to be a phantom, an artifact of the way the data had been processed. In 2021, a different team detected a candidate planet around Alpha Centauri A using a new infrared technique. This world, tentatively called C1, would orbit within the habitable zone. It might be roughly the size of our planet or slightly larger. The detection has not yet been confirmed and could still vanish under further analysis. Even if it exists, the gravitational complexity of the system makes the long-term stability of any such planet uncertain. Computer simulations have shown that planets in this region might survive for hundreds of millions of years before being disturbed. By cosmic standards, this is short. Earth has been quietly stable for over 4 billion years. A short-lived planet is a bad place to look for advanced life. Evolution needs time. Earth required billions of years of relatively peaceful conditions to develop animals and intelligence. A planet that gets gravitationally kicked around every few hundred million years rarely catches its breath long enough for biology to grow complex. The Alpha Centauri pair also has another effect. Both stars are roughly similar to our home star, but slightly different in mass and brightness. Their combined glare lights up any planet in unusual ways. Imagine a sky with two suns of different colours, sometimes both visible, sometimes only one. Daylight that flickers in intensity as the stars move in relation to each other. For a crew that journeyed 100 years to study these worlds, the rewards might be strange enough to seem worth the trouble. But the bigger question is whether stable, life-supporting planets exist in this neighbourhood at all. Computer simulations of planetary motion in the Alpha Centauri system have been running for decades. Astronomers feed the gravitational data into supercomputers and watch what happens to hypothetical planets across millions of simulated years. The results are mixed at best. Around the smaller component, Alpha Centauri B, simulations show that planets in the habitable zone can sometimes survive for long periods. Sometimes they get disrupted within tens of millions of years. The outcome depends sensitively on the exact starting conditions, which are unknown. This is a mathematical mess. The system is what physicists call chaotic. Small differences in starting conditions lead to wildly different outcomes over time. A planet that survives in one simulation might get ejected in another simulation that started with conditions slightly off by a fraction of a percent. Astronomers cannot precisely measure the starting conditions of real planets in the Alpha Centauri system. They can only observe the system as it is today. Reconstructing its full gravitational history requires assumptions, and different assumptions lead to different conclusions. Some studies suggest there should be at least 1 or 2 stable planet zones around each of the bigger stars. Others suggest the gravitational chaos has cleared most of the system. The truth lies somewhere in between, and it might require direct observation to settle. That observation is hard. Planets at Alpha Centauri are very dim compared to their stars. Detecting them requires either watching for the slight wobble of the star caused by planetary gravity, or observing the star slightly dim as a planet passes in front of it. Both methods are hard at this distance, despite the system being our closest neighbour. The James Webb Space Telescope, launched in 2021, might eventually image planets in the system directly. Other future missions are being designed specifically to hunt for planets at Alpha Centauri. The most ambitious is a proposed space telescope that would use a giant starshade to block the light of the bright stars, revealing any planets nearby. Even if planets are found, the question remains whether they could host life. The 2 bigger stars are old, both estimated at between 4 and 7 billion years. That is roughly the age of our home star. There has been time for life to evolve, if conditions allowed. But conditions in this triple star system are likely turbulent. Planets here have experienced shifting orbits, possibly close encounters with each other, and constant gravitational stirring from the binary pair. Life would have had to weather these disruptions for billions of years. Some astronomers argue that triple systems like Alpha Centauri are actually decent places for life. The presence of multiple stars distributes warmth more evenly. Stars stabilize each other against certain kinds of stellar instability. The longer histories of such systems give life more time to develop. Other astronomers disagree. They point out that the gravitational chaos rarely allows for the kind of long-term orbital stability that complex life seems to require. Earth's history of relative quiet might be a rare cosmic accident, and Alpha Centauri likely never offered such peace. Until we actually visit, we will not know, and visiting is exactly what every plan we have keeps failing to make possible. For now, the closest star system remains a tantalizing mystery. We can see it. We can study it from afar. We cannot reach it. The next dream is to bypass the propulsion problem entirely with the most exotic substance in physics, but its production requires resources beyond imagination. Antimatter is the most concentrated form of energy that physics allows. When a single particle of antimatter touches a single particle of normal matter, the two annihilate each other completely. Every speck of their combined mass converts directly into pure energy. Nothing is wasted. Nothing is left behind. The amount of energy released is staggering. 1 gram of antimatter mixed with 1 gram of regular matter releases the energy of roughly 43,000 tons of TNT. That single gram could power a small city for hours, or push a starship to a respectable fraction of light speed. This is why antimatter has captured the imagination of every serious interstellar designer. With enough antimatter, the trip to Alpha Centauri becomes plausible within a human lifetime. A few hundred kilograms of fuel could push a moderate starship to perhaps 50% of light speed, completing the journey in about 10 years. The math finally smiles. The dream finally seems reachable. Then reality steps in. Antimatter does not occur naturally in any usable quantity. Trace amounts exist in the cosmic ray background, in certain types of radioactive decay, and in the upper atmosphere when high-energy particles collide with air molecules. None of these sources can be harvested at meaningful rates. To get antimatter, humans have to make it. The process involves smashing high-energy particles into a target inside a particle accelerator. Some collisions produce small quantities of antimatter, which must then be carefully captured before they touch any normal matter and annihilate. The largest particle accelerators on Earth, like the Large Hadron Collider in Switzerland, produce antimatter as a side effect of their experiments. The total amount produced worldwide every year is measured in trillionths of a gram. Pause on that number, trillionths of a gram per year, across every facility on the planet combined. To fuel a single starship, perhaps a few kilograms of antimatter would be needed. To produce that quantity at current rates would take longer than the age of the universe. It is not even a problem of needing more time. The numbers are so absurd that no amount of patience could solve them. Producing antimatter is also enormously inefficient. The energy required to make 1 gram of antimatter is millions of times greater than the energy released when that gram is later annihilated. From a practical standpoint, antimatter is a battery that costs millions of times more to charge than it returns when used. Why bother then? Because it stores energy in an incredibly compact form. A starship cannot carry the equivalent in conventional fuel, because there is no way to store that much energy in a manageable mass. Antimatter is a way to compress impossible amounts of energy into a small package, even if making the package is itself impossibly expensive. There is also the storage problem. Antimatter cannot touch any normal matter, including the walls of its container. The only way to hold it is in magnetic traps, where charged antiparticles are suspended in a vacuum by powerful magnetic fields. These traps require constant power. If the power fails for even an instant, every gram of stored antimatter detonates with the force of a hydrogen bomb. Carrying tons of antimatter on a starship means carrying a continuously armed nuclear arsenal that detonates the moment any system glitches. One bad capacitor, one micrometeorite hit, one human error, and the entire mission disappears in a flash visible from across the galaxy. There are designs that propose using less antimatter as a catalyst for fusion reactions, reducing the required quantity to just a few milligrams. Even those designs require quantities 1,000 times greater than humanity has ever produced. And the fusion reactions they trigger are still not fully understood. If antimatter is too expensive, perhaps fusion alone can do the job, but that path has its own paper-only frustrations. Fusion is the process that powers every star in the universe. Hydrogen atoms slam together under enormous pressure and temperature, fusing into helium and releasing tremendous amounts of energy. A single gram of hydrogen fuel, fully fused, releases the energy of about 30,000 gallons of gasoline. Engineers have dreamed of fusion-powered spacecraft for nearly 70 years. The numbers are beautiful. A fusion engine could potentially reach exhaust velocities of about 1 to 10% of light speed, depending on the exact reaction used. A starship using fusion propulsion could reach Alpha Centauri in perhaps 50 to 100 years. This is far better than chemical or fission rockets. It is achievable within roughly 2 human generations, which makes generation ship designs at least conceivable. The fuel for fusion is abundant. Hydrogen is the most common element in the universe. There is enough of it to power humanity's interstellar dreams forever. There is just one inconvenient detail. Controlled fusion does not work yet on Earth. Researchers have been trying to harness fusion since the 1950s. Multiple multi-billion-dollar projects have come and gone. The largest current effort is ITER, a giant international fusion reactor being built in southern France. Construction began in 2007. The first plasma is now expected sometime in the late 2030s. Net energy production is hoped for by the 2040s. That is for a building-sized reactor on Earth, with stable foundations, infinite cooling water, abundant power supplies, and skilled engineers nearby. After more than 70 years of effort, nobody has yet built a practical fusion reactor that produces more energy than it consumes for sustained operation. Now imagine shrinking that reactor down to fit inside a spacecraft. The engine has to be light, compact, reliable, and able to run for years or decades without maintenance. It must produce thrust by directing fusion products out the back of the ship at near light speed. It must do this in zero gravity, in deep space, with no supply chain and no repair options. Several specific designs have been proposed. The Daedalus project, sketched out in the 1970s by the British Interplanetary Society, imagined a fusion pulse drive using pellets of fuel ignited by electron beams. The design called for a 5-mile-long ship weighing 50,000 tons. The fuel for one mission would have required mining the atmosphere of Jupiter for helium-3, which itself would have taken centuries. Project Longshot, proposed in the 1980s by NASA and the United States Naval Academy, imagined a more modest fusion ship that could reach Alpha Centauri in about 100 years. It still required quantities of fuel and engineering precision well beyond anything we can build today. Project Icarus, started in 2009, is an updated version of the Daedalus concept. It uses modern computational tools to refine the design. Even Icarus admits the technology is decades away, possibly centuries away, from being realizable. The basic problem is plasma confinement. Fusion requires temperatures of millions of degrees. At those temperatures, nothing solid can contain the reaction. The plasma has to be held in a magnetic bottle that prevents it from touching any walls. Building a magnetic bottle that works reliably for decades, while also producing useful thrust, has never been done. Some designs avoid this by using inertial confinement. Tiny pellets of fuel are imploded by lasers or particle beams, fusing in microsecond bursts. The Daedalus design used this approach. In theory, it works. In practice, designing the laser systems, the pellet feeding mechanism, and the magnetic nozzle that directs the explosion outward all remain unsolved. If fusion is hopeless, perhaps physics offers a deeper trick. Wormholes have always been the favourite shortcut in science fiction. The math even allows them in theory. The reality is something else entirely. Wormholes are tunnels through the fabric of space-time. Instead of travelling the long way through normal space, a ship enters one end of a wormhole and exits the other end somewhere far away. If the wormhole connects Earth to Alpha Centauri, the trip takes essentially no time at all. It sounds like pure fantasy. Surprisingly, wormholes are mathematically allowed by Albert Einstein's general theory of relativity. The equations of gravity describe how mass and energy bend the geometry of space and time. Under the right conditions, the geometry could fold back on itself, creating a shortcut between two distant points. The first serious wormhole solutions were worked out in 1935 by Einstein and physicist Nathan Rosen. They imagined a connection between 2 points in space-time that could allow instant travel between them. The solutions became known as Einstein-Rosen bridges, the original wormhole concept. Later physicists, especially Kip Thorne in the 1980s, refined the math. Thorne showed that a wormhole could in principle be made traversable, meaning a ship could pass through without being crushed or killed by gravity. The math allows it. The geometry is consistent. Now for the catch. To hold a wormhole open, an enormous amount of what physicists call exotic matter is required. Exotic matter is a hypothetical substance with negative energy density. It has properties unlike anything ever observed in nature. Normal matter pulls on space and bends it inward. Exotic matter would push space outward, creating the kind of pressure needed to keep a wormhole from collapsing. Nobody has ever found exotic matter. Nobody has ever made it. There is no clear experimental hint that it exists at all in the form needed for wormhole construction. Some quantum effects produce small amounts of negative energy under very specific conditions, like the Casimir effect between two close metal plates. The total amount produced is laughably small compared to what wormhole engineering would require. The amount needed is also staggering. To hold open a wormhole large enough for a starship, calculations suggest you would need exotic matter with the negative mass equivalent of an entire planet, possibly even a star. Producing or finding such a quantity is far beyond anything currently imaginable. There is also a stability problem. Even if exotic matter could be obtained and a wormhole created, the structure would be incredibly fragile. Any normal matter passing through could disrupt the negative energy balance and cause the wormhole to collapse, potentially with catastrophic results for whatever ship was inside. Then there is the location issue. Where exactly would the other end of the wormhole appear? If you somehow created one end on Earth, the other end would have to be physically constructed at Alpha Centauri, which means someone, or something, has to travel there first to build it. The wormhole solves the travel problem only if you have already solved it. Naturally occurring wormholes have been speculated about. Some scientists have proposed that primordial wormholes might have been created in the very early universe and could still exist somewhere. There is no observational evidence for any such object. They are mathematical possibilities, not confirmed phenomena. Even with all these obstacles, wormholes remain a popular topic in physics research. They appear in discussions of quantum gravity, theories of consciousness, and time travel. They are also a favourite plot device in science fiction films. As a serious mode of interstellar transport, however, they remain entirely theoretical. If wormholes are too exotic, what about the famous warp drive? Surely the science fiction staple has some basis in reality. As it turns out, yes, but the price is unimaginable. The warp drive idea moved from pure fiction to serious physics in 1994, when Mexican theoretical physicist Miguel Alcubierre published a paper describing how a ship might travel faster than light without breaking any rules of relativity. The trick was beautiful. Instead of moving the ship through space, you move space itself. Alcubierre showed mathematically that a region of spacetime could be contracted in front of a vehicle and expanded behind it. The vehicle inside the warped region would not actually be moving relative to its local space. It would be carried along by the warping itself, like a surfer riding a wave. There is no speed limit on the expansion or contraction of space. The universe itself expanded faster than light during a brief period after the Big Bang, so a ship inside an Alcubierre bubble could effectively travel between stars in a few weeks, even though no signal inside the bubble would ever exceed light speed locally. Relativity is preserved. The math works. The physics community was excited. Briefly, then the energy requirements were calculated. The original Alcubierre solution called for enormous amounts of negative energy density far beyond anything attainable. Estimates suggested that the energy needed to warp a small bubble around a single ship might equal the entire mass energy of Jupiter, or more, possibly the total mass energy of the entire visible universe. Later refinements by other physicists reduced the requirement. By tweaking the geometry of the bubble, the energy needed could potentially be lowered to the equivalent of a planet, then a moon, then perhaps a few hundred kilograms of negative energy, still far more than anything humans could produce. There is also the same exotic matter problem that wormholes face. The warp drive requires negative energy density to function. Without exotic matter, there is no way to actually create the warping geometry. The math allows it. The physics, as currently understood, does not provide the materials. Other issues have emerged over time. A warp bubble travelling at faster than light speeds would accumulate enormous amounts of high-energy particles at its leading edge. When the bubble collapses at its destination, those particles would be released as a powerful gamma-ray burst, potentially sterilizing the very world the ship was visiting. Arriving in the Alpha Centauri system might mean accidentally vaporizing it. There is also the issue of causality. Faster-than-light travel, in some scenarios, allows the construction of time machines. Small errors in the warp bubble could result in the ship arriving before it left, opening up paradoxes that physicists generally consider forbidden by deeper laws of nature. Despite these problems, research continues. NASA has funded small experimental work on warp-related concepts, more as a way to test the boundaries of physics than as a near-term engineering project. Some recent papers have proposed alternate geometries that might work without exotic matter, but these remain speculative. The warp drive is therefore in roughly the same status as the wormhole. It might be possible. The math allows it. The physics, as currently practiced, cannot build it. We do not even know if the substance required exists, let alone how to manufacture it. For now, faster-than-light travel remains a fantasy with mathematical legitimacy. It is exactly the kind of trick that an advanced civilization might one day master, perhaps thousands of years from now, perhaps never. We have no idea. If physics offers no help, perhaps money can solve the problem. Surely with enough resources, humanity could brute force its way to Alpha Centauri. The answer reveals just how poor we really are. Forget the technical problems for a moment. Pretend the engineering is solved. Pretend fusion drives work, radiation shielding is perfect, the crew is psychologically stable. Now, ask a simple question. How much would the actual mission cost? The answer is enough to bankrupt civilizations. The Apollo program, which sent a dozen humans to the moon, cost about $25 billion in 1960s money. Adjusted for inflation, that is roughly $250 billion today, for a journey of around 240,000 miles lasting about a week. Alpha Centauri is nearly 100 billion times farther away than the moon. The mission would last decades or centuries instead of days. The technology required is far beyond anything available. The crew, if any, would need life support for entire lifetimes. Various estimates have been published over the decades. They range wildly depending on the propulsion method assumed and the size of the ship. A modest robotic probe, similar in scale to Voyager but with much faster propulsion, might cost between $50 billion and $500 billion. That is just for the probe itself, not the infrastructure needed to launch it or support it. A laser-push sail mission like Breakthrough Starshot is estimated at perhaps $10 to $20 billion for the laser array alone. The probes themselves could be relatively cheap, but the array is the dominant cost. Some estimates put the full project cost above $100 billion when all infrastructure is included. A fusion-powered crewed ship would be in another economic universe entirely. The ship itself would weigh thousands or millions of tons. Building it in space would require an industrial base on the moon or in orbit that does not yet exist. Estimated costs run into the trillions of dollars, possibly tens of trillions. For comparison, the entire annual gross domestic product of the United States is about $27 trillion. The annual GDP of the entire world is about $100 trillion. A single crewed interstellar mission could plausibly cost a significant fraction of the world's total economic output for a year. Spread across decades of construction, this becomes more manageable. $1 trillion over 30 years is about $33 billion per year. The United States alone spends more than that on its military annually, so in principle, the budget exists. The political will does not. No nation has ever committed to a project of this scale. The International Space Station, which is the most expensive space project ever built, cost about $150 billion across multiple countries over more than 2 decades. A Starship would cost many times that and produce no economic return for centuries. Private interests have shown some interest. Yuri Milner's funding of Breakthrough Starshot demonstrates that wealthy individuals can sponsor early research. But even the richest person on Earth lacks the resources to build a real interstellar mission. The combined wealth of every billionaire on the planet would not be enough to fund a full crewed mission to Alpha Centauri. There is also the question of return on investment. A Starship mission produces no commercial benefit for the people funding it. The crew, if any, will not return to Earth for over a century. Any data collected will arrive years after it is gathered. There is no oil to import, no tourism to attract, no products to sell. The mission would be a pure act of curiosity, funded by a civilization that has decided exploration matters more than profit. Whether any human society actually values exploration, that highly remains an open question. The honest answer to this is dispiriting. Even if every nation pooled resources, the cost would still strain economies for decades, and the political reality is far worse than the financial reality. In the 1960s, the United States government spent over 4% of its federal budget on space exploration. The Apollo program was a massive national effort, supported by polls showing public enthusiasm. Astronauts were celebrities. Rocket launches were national events. Today, NASA receives less than 0.5% of the federal budget. The agency's portion of government spending has declined steadily for decades. Crewed, deep space missions have not happened since 1972, when the last Apollo astronauts returned from the Moon. The pattern is similar in other nations. Russia inherited the Soviet space program, but has steadily reduced its space ambitions. Europe has a respectable space agency, but has never seriously proposed crewed missions beyond Earth orbit. China has expanded its program in recent decades, but focuses on national prestige projects rather than long-term exploration. India and Japan have growing programs but limited budgets. Why did the dream fade? Several reasons. The first is the simple absence of urgency. The Apollo program was driven by Cold War competition with the Soviet Union. Beating the Russians to the Moon was framed as a matter of national security and ideological prestige. Once the Soviets gave up the lunar race, the political fuel for further expansion evaporated. The second is cost. Space exploration is expensive and budgets are always under pressure from competing priorities. Healthcare, education, infrastructure, and defense all demand huge portions of national spending. Sending a probe to another star with no immediate benefit ranks low on most political priority lists. The third is perceived risk. Crewed space missions carry political danger. The Challenger disaster in 1986 and the Columbia disaster in 2003 each killed 7 astronauts and triggered major investigations. Politicians who push for ambitious missions know that any failure could damage their careers. Robotic missions are safer. Even better is no mission at all. The fourth is shifting priorities. Modern governments increasingly focus on near-term issues like climate change, economic competitiveness, and domestic concerns. Long-term visionary projects are harder to justify when voters demand immediate results. A Starship that arrives in 200 years offers no votes today. There have been exceptions. NASA's New Horizons mission flew past Pluto in 2015. The Voyager probes continue to operate and return data from interstellar space. The James Webb Space Telescope launched in 2021 and has produced spectacular discoveries. These projects show that ambitious science is still possible, but none of them approach the scale required for crewed interstellar travel. The closest thing to an interstellar mission currently funded is research, not hardware. Breakthrough Starshot, mentioned earlier, exists primarily as a research consortium studying the feasibility of laser sail propulsion. NASA has occasionally funded small studies of fusion drives, antimatter storage, and warp drive theory through its NASA Innovative Advanced Concepts program. These are small grants, totaling a few $1,000,000 per year, designed to keep ideas alive rather than to build anything real. Some space advocates argue that private industry will pick up where governments have left off. Companies like SpaceX have demonstrated impressive capabilities for launching satellites and astronauts to Earth orbit and the Moon. Elon Musk has spoken openly about wanting to send humans to Mars and beyond. But even SpaceX has not seriously proposed an interstellar mission. The technology gap is too large, the economic incentives are too weak, the timeline is too long for any company to plan around. So the dream of reaching Alpha Centauri has quietly been deferred. Officially, it remains a future goal. Practically, no nation or company has committed real resources to making it happen, and the political timeline involved is even more depressing. A serious crewed mission to Alpha Centauri would take a minimum of 100 years to complete. More realistic estimates suggest 200 to 500 years, depending on the propulsion method. Some designs based on slower technologies stretch the timeline to 1,000 years or more. This timeline is incompatible with any human political system that has ever existed. Consider how long countries last. The United States is 250 years old. The current British political structure dates to the late 17th century. France is on its fifth republic since the late 18th century. Most modern nations are less than 200 years old in their current form. Many, especially in Africa and Asia, have existed for less than a century. Now imagine launching a mission whose purpose stretches across multiple successor nations. The country that launches the ship may not exist when it arrives. Borders will shift. Ideologies will rise and fall. The political descendants of the launching civilization may have no interest in continuing the mission. Funding alone is a nightmare. A Starship project requires uninterrupted financial support across centuries. Every annual budget cycle is a chance for the project to be cancelled. Every political transition is a chance for priorities to change. Across 200 years, there might be hundreds of governments, each with different agendas. The Apollo program survived for about a decade before being terminated by political pressure. The Space Shuttle ran for 30 years before being cancelled. The Hubble Space Telescope nearly died multiple times due to budget fights. These are short timelines compared to what an interstellar mission requires. Multinational projects help spread the political risk. The International Space Station is supported by 15 countries. If any one of them pulls out, the others can usually keep going. But even multinational projects struggle. Russia has been an unreliable partner since 2022. China is excluded from the station entirely. Future political shifts could break apart even the strongest cooperative agreements. Then there is the question of cultural continuity. The crew of a generation ship would launch with values and beliefs from the early 21st century. Their descendants, 4 or 5 generations later, would arrive at Alpha Centauri with values shaped by an entirely different cultural context. They might not share the worldview of their original sponsors. They might decide to do something different with the mission than what was originally planned. History is full of examples of long-term projects that lost their original meaning. Medieval cathedrals took centuries to build, and many were modified or completed in styles totally different from the original designs. Religious orders that started one way ended up another. Empires founded with grand visions often collapsed into very different institutions before they fell apart entirely. Now stretch that across a Starship mission. The original launch team dies. Their children are taught to continue the mission. The grandchildren have only second-hand knowledge of why the mission matters. The great-grandchildren live entirely inside the ship, with no memory of Earth or its peoples. By the time the ship arrives at Alpha Centauri, the crew might be more loyal to their ship culture than to any planet-bound civilization. There is also the risk that Earth itself might not survive long enough to support the mission. Climate disruption, nuclear war, pandemic, asteroid impact, or any number of other disasters could collapse global civilization within centuries. A Starship in flight might suddenly find itself with no support back home. Mission control might go silent. The flow of cultural updates might stop. The crew would have no choice but to push on alone or turn back to a dying world. Worse, the world they left might be unrecognizable when their children arrive. The next chapter takes that possibility seriously. A spacecraft launched today toward Alpha Centauri, even with optimistic propulsion technology, would not arrive for at least 100 years. The radio signals confirming arrival would take another 4 years to reach Earth. Total turnaround time from launch to confirmation of success is at least a century and a half. A great deal can happen on Earth in a century and a half. Consider what has changed in the last 150 years. In 1875, electricity was a curiosity. Most of the world had never seen a light bulb. There were no cars, no planes, no radios. 2 world wars had not happened. Half the world's countries did not exist. The total human population was about 1.5 billion, a fraction of today's 8 billion plus. Now project forward. What might Earth look like a century and a half from now? Climate scientists already warn of significant disruption from human-caused warming. Sea levels are rising. Extreme weather is becoming more common. Some regions may become uninhabitable due to heat or drought. Mass migration could destabilize governments. Resource conflicts could escalate. These risks are not certainties. Humanity might solve climate change. Technology might bail us out. Society might adapt successfully. But the risks are real, and they grow over longer timescales. Other threats also lurk. Nuclear weapons remain in the arsenals of 9 countries. Engineered pandemics, while still hypothetical at large scale, are becoming more conceivable as biotechnology advances. Artificial intelligence raises questions about human survival in ways we are only beginning to understand. Asteroid impacts, while rare, are not impossible. Any of these scenarios could disrupt or destroy the civilization that launched a starship. By the time the spacecraft arrives at Alpha Centauri, the world it left behind might no longer exist in any recognizable form. The crew would have no Earth to report back to. This is not just a depressing thought experiment, it has practical consequences for any mission planning. A starship needs continuous support from Earth for monitoring, problem solving, and morale. If Earth goes dark, the crew loses contact with everything that defined their purpose. Some planners have suggested that the ship should be designed to operate completely independently, just in case. The crew would be trained to expect that Earth might fall silent at any moment. They would be prepared to continue the mission, or even establish a new branch of humanity at Alpha Centauri, regardless of what happens on the home planet. This raises a chilling possibility. The first interstellar voyage might not be a one-way exploration. It might be a one-way evacuation. A small group of humans escaping a dying Earth, carrying the seeds of the species to a new world. Whether that new world can actually support them is another question, given the issues already discussed. There is also the question of motivation. Why would anyone fund a Starship mission knowing that the launching civilization might not survive to see it succeed? The answer, traditionally, is that exploration matters even if the explorers never return. Knowledge has value beyond its immediate use. The act of reaching out to the stars is itself a statement about what humanity is, but this kind of long-term thinking is rare. Most political and economic systems are built around short timeframes: 5-year plans, quarterly earnings, election cycles. Asking a civilization to commit centuries of resources to a project whose success depends on conditions far beyond planning is asking for a kind of patience that history has rarely shown. If Earth survives long enough to launch the mission, and somehow continues to support it across the journey, the next question becomes whether sending humans on a one-way trip is even ethically defensible. A crewed mission to Alpha Centauri is, with current technology, almost certainly a one-way journey. The fuel needed to return to Earth would essentially double the size of the ship and the cost of the mission. Most realistic plans assume the crew goes there to stay. This raises serious ethical questions that no agency or government has fully addressed. The first issue is informed consent. Volunteers for a one-way mission can technically consent to give up Earth forever. They sign agreements. They take oaths. They commit fully to the project. Yet how informed can such consent really be? Nobody has ever experienced what they are agreeing to. The psychological effects of a 100-year voyage in deep space are unknown. The realities of life on a tidally locked alien world are unimaginable. A volunteer might genuinely think they understand what they are signing up for, only to discover, 20 years into the mission, that the experience is unbearable. Once committed, there is no way back. They are stuck for the rest of their life. The second issue concerns the children. Generation ships, by definition, involve people who never chose to be on the mission. The children of the original crew are born inside the ship. They have no memory of Earth. They have no option to leave. Their entire existence is shaped by decisions their grandparents made before they were conceived. Is it ethical to bring children into a life of permanent confinement? Some philosophers argue yes, since children always inherit circumstances they did not choose. People are born into poverty, into war zones, into difficult families, all without consent. A generation ship is just another circumstance. Others argue no, because the level of confinement and the absence of any escape route make it qualitatively different from normal life. The third issue is the burden on the destination. If humans arrive at a world that has its own ecosystem, even microbial, the mission might contaminate or destroy a unique form of life. Earth's history is full of examples of species being wiped out by introduced organisms. A starship full of bacteria, viruses, and human cells could be devastating to alien biology that has never encountered such things. Conversely, alien microbes could be deadly to the crew. Without proven antibodies, even a mild local pathogen could wipe out the entire mission within weeks. Quarantine protocols might be impossible to implement at the scale required. The fourth issue is the long-term goal. Why exactly are we sending people? To explore, to establish a colony, to save humanity from a dying Earth. Each motivation comes with different ethical implications. A scientific mission with a small crew is one thing. A colonization effort that intends to genetically modify humans for the new environment is something quite different. Some philosophers worry about the very idea of spreading humanity to other star systems. They argue that we have not yet demonstrated the wisdom to manage even one planet successfully. Bringing our problems to Alpha Centauri might not be a triumph, but a curse. We might infect the rest of the galaxy with the same destructive patterns we exhibit on Earth. Others argue the opposite. They claim that establishing a second home for humanity is essential insurance against extinction. A single-planet civilization is fragile. A multi-planet civilization is far more robust. The ethical case for backup is strong, even if the methods are imperfect. There is no agreed answer. The ethics of interstellar travel are still being worked out, mostly by philosophers and bioethicists writing papers that no government reads. By the time the actual mission becomes possible, the ethical discussion may need to start over from the beginning, because the technology and circumstances will have changed. If humanity ever does succeed in sending a mission, the most important question becomes what they would actually find when they arrive. Imagine the impossible has happened. The mission was funded, the technology worked, the crew survived, the ship has slowed down and entered the Alpha Centauri system. After a century or more of travel, it is finally time to look around. What do you actually see? The view is dominated by 3 points of bright light instead of one. Two main stars, Alpha Centauri A and B, dance around each other every 80 years. Both are roughly similar to our home star, though A is slightly bigger and B slightly smaller. The third star, Proxima Centauri, is a distant red companion, much farther out and far dimmer. If the mission targets the binary pair, the ship enters a region with two suns. Daylight on any nearby planet would be different from anything humans have experienced. Sometimes both stars would be visible, lighting the sky with double shadows. Sometimes only one would be up, the other on the far side of the planet's orbit. The colours would be strange, with one star slightly more yellow than ours and the other slightly more orange. If any planets exist around the binary, they would have unusual orbits. The gravitational pull of two stars makes simple, regular orbits rare. Planets here might wobble in complex paths, with seasons that vary in length and intensity in ways no Earth life ever evolved to handle. Or, if the ship targets Proxima Centauri instead, the view is very different. A single small red star, much dimmer than our local one. The planet Proxima b, if it exists in confirmed form, would be tidally locked. The ship would observe a world with eternal day on one side and eternal night on the other. Whatever planets exist would likely be radically different from Earth in important ways. Their atmospheres might be too thick or too thin. Their surface chemistry might be incompatible with human biology. Their magnetic fields might be too weak to protect anyone outside a sealed habitat. Their stars might flare too violently to step outside without protection. In the best case, the mission finds one or more rocky planets with thin but breathable atmospheres, some liquid water, and tolerable temperatures in certain regions. The crew could potentially walk on the surface in environment suits. Long-term colonization might be feasible with significant infrastructure. In the worst case, the mission finds airless, irradiated rocks. Useful for resources, perhaps, but not for living. The crew would have to remain inside the ship or build sealed habitats. They would never feel local sunlight on their skin. They would never breathe outside air. They would have travelled 100 years to reach a glorified asteroid. The most exciting possibility, of course, is finding signs of a life. Even microbial life would be the discovery of the millennium. Confirmation that biology exists beyond Earth would transform every aspect of human thought. Religion, philosophy, science, all would be shaken to their foundations. But finding life is itself complicated. Alien biology might be so different from Earth biology that we would not recognize it at first, or we might be so afraid of contamination that we never get close enough to study it properly, or we might inadvertently destroy it during our first attempts at investigation. Intelligent life is much less likely. The Alpha Centauri system shows no signs of artificial radio transmissions, large-scale engineering, or other markers of advanced civilization. We have been listening for decades. The galaxy seems quiet, at least in our nearest neighbourhood, so the most realistic expectation is barren or microbial worlds, not the lush forests of science fiction, not the human-friendly planets of space operas, just rocks, perhaps with traces of strange chemistry, possibly with primitive biology lurking in some hidden corner. This sobering reality leads to one final uncomfortable conclusion about humanity's interstellar future. After analysing every problem, every limit, every barrier, a difficult thought begins to settle in. Maybe interstellar travel by humans is not just hard. Maybe it is impossible. This is not a popular conclusion. Most people, especially space enthusiasts, hate hearing it. The dream of humanity expanding to the stars is deeply embedded in modern culture. Countless books, films, and television shows have built their entire universes around the assumption that we will eventually travel between stars as easily as we travel between cities today. But every barrier discussed so far points in the same direction. The propulsion problems are not minor engineering issues. They are fundamental limitations imposed by physics itself. The crew problems are not solvable with better training. They reflect the basic biology of human beings. The economic costs are not tweakable through clever financing. They reflect the actual scale of the undertaking. Even with technologies 100 years more advanced than today, the challenges may remain insurmountable. Light speed is not negotiable. The vastness of interstellar space is not exaggerated. The fragility of human bodies in extreme environments is not a matter of toughening up. Some serious thinkers have already accepted this conclusion. Astrophysicist Ethan Siegel has written that human interstellar travel may simply never happen. Astronomer Adam Frank has noted that the gap between technological optimism and physical reality is widening, not narrowing. Physicist Kip Thorne, who helped develop the math of wormholes, has acknowledged that the energy requirements may be permanently beyond reach. There are several reasons why this conclusion might be correct. The first is the Fermi paradox. If interstellar travel were practical, the galaxy should be full of evidence. Older civilizations should have spread across the stars long ago, leaving signs we could detect from Earth. Yet decades of searching have found nothing. The simplest explanation is that interstellar travel is genuinely impossible, even for civilizations far more advanced than ours. The second is the historical pattern of physics. Many things that seemed impossible to people in the past turned out to be possible. Many things that seemed possible turned out to be impossible. Faster than light travel falls in the latter category. The more we learn about the universe, the more solid the light speed barrier appears. The third is the economic logic. Even if interstellar travel becomes technically possible, the cost-benefit analysis may never work. Earth and the solar system contain plenty of resources for a long time to come. There is no economic reason to spend trillions of dollars on a mission that produces no return for centuries. Without economic motivation, the projects rarely get funded. The fourth is the timeline mismatch. Human civilizations have rarely survived for more than a few thousand years in any recognizable form. Interstellar missions require political stability across timescales longer than any human institution has ever maintained. The probability that a civilization will both develop the technology and maintain the will to use it across hundreds of years may be very low. This does not mean nothing will ever cross the gap. It just means that whatever crosses might not be human and might not be biological at all. If humans are unlikely to ever physically reach Alpha Centauri, what will? The answer, in all probability, is robots, machines, and light itself. Robotic probes are far better suited to interstellar travel than humans. They do not need food. They do not need oxygen. They do not need protection from radiation in the same way biology does. They can be built to last centuries, and they can be designed to operate without supervision. A small probe is much easier to accelerate to high speed than a giant generation ship. The breakthrough Starshot concept, despite its many problems, represents the most realistic path forward. Tiny probes, accelerated by lasers, racing to Alpha Centauri at 20% of light speed, returning images within a few decades. This is the kind of mission humanity might actually fund and complete within the next century. Future probes might be more ambitious. They could carry small artificial intelligence systems capable of analysing data, making decisions and communicating findings without constant guidance from Earth. They could potentially manufacture small landers from local resources, sending detailed surface data back home. Some designs even envision self-replicating probes that could build copies of themselves at the destination, expanding exploration outward in waves. Light is the other ambassador. Beyond physical objects, humanity already sends signals across the galaxy in the form of radio transmissions and laser communications. Every television broadcast, every cell phone call, every Wi-Fi signal leaks a tiny amount of energy into space. Some of it has already reached nearby stars. Anyone listening at Alpha Centauri with the right technology could, in principle, detect the radio glow of Earth. We could deliberately transmit messages too. With powerful enough lasers or radio antennas, we could send information towards specific stars at the speed of light. This requires no spacecraft, no fuel, no decades of travel. It is the cheapest form of interstellar communication, and it is already within our capabilities. Of course, this is not the same as physically reaching the stars. A photon arriving at Alpha Centauri is not a colony. A radio signal carrying human data is not a human presence. But it is contact of a kind. It is the first wave of human influence reaching out beyond our local neighbourhood. There is a deeper reason why robots might be the right ambassadors. They can be designed for the journey in ways humans cannot. A probe does not need to be a generalist. It can be optimized purely for survival and observation in deep space. Its architecture can be radically different from anything biological. Future probes might not even be made of matter as we know it. Some theorists have proposed using lasers to imprint information on quantum systems that could be reconstructed at the destination. The information itself travels, rather than the physical object. This is far beyond current technology, but it suggests a future where the entire concept of interstellar travel is rethought. There may also be a long arc to consider. Humanity, in its current biological form, might never reach Alpha Centauri. But our descendants, modified or augmented in ways we cannot yet imagine, might find ways to make the journey. They might be partially mechanical. They might be uploaded consciousnesses inside computers. They might be entirely artificial beings that grew out of human civilization. Whether such future entities would still count as us is a philosophical question with no easy answer. They would carry our cultural heritage, our scientific knowledge, our memories of Earth. They might consider themselves the continuation of the human story, or they might be something genuinely new, only loosely connected to the species that gave them birth. Either way, the stars are unlikely to remain forever beyond reach. They may simply belong to a kind of explorer very different from the warm-blooded creatures looking up at the sky tonight. The dream of touching another star endures, even as its form changes. The gap to Alpha Centauri may never close for humans of flesh and bone. The journey may belong to others, and perhaps that, in the end, is enough.